Yeah. Test. Test. This is me. Can you hear me? Yeah. Test for the video share. You cannot hear me? But maybe because I was talking there. I mean, can you hear me here? Can you hear me? If I now is it fine? The source of your where is it getting the audio from? You're using the device audio. Now it should get because usually it's like shows something, right? No, yeah, blah, 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 blah. Right? It shows like it doesn't green. Show anything. Yeah, so it's your device problem, I think. Funny because I usually I do Zoom this way. You know that. Like you can try a few more times. Oh, could you try if you put the like if you record the sound from your laptop? Yeah. No, I need my laptop. Aha. You are the okay. I see. I can put my laptop. Okay. So I need to run to the other room. I'll come back and check in 5 minutes. All right. Sounds good. And I think we're good. Are we? Okay, let's play. Should I start? So, hello, thanks everyone for coming, especially since you could instead be strolling London in this sunny weather. So, congratulations. So, I'll be talking about machine learning meets program synthesis, which is a bit of an ambiguous title. It doesn't exactly say whether program synthesis will help machine learning or the other way around. So we'll see what I really mean by that. And a lot of this tutorial will be about, or not about, rather against LLMs, large language models, and why there's more to it for program synthesis. So of course, they're taking over the world, including and in particular program synthesis. So is program synthesis solved? I guess you know the answer to that question. No, and that's why we're here. But let's see exactly why. And the question that I would like to kind of address in this tutorial is how can we, and by we I mean in a very large sense, program language people, formal methods, contribute to program synthesis, and in particular the rise of program synthesis with machine learning. So I'm not denying or negating the use of machine learning. I really think that this is a great potential for program synthesis, but LLM is not the end of the story for program synthesis. So this is kind of the message that I want to give or discuss. And there's an interesting terminology shift. For decades, we've been talking about program synthesis. And program synthesis in many people's minds, this is related to inductive programming, logic programming, and it has roots in logical settings. And together with LLMs, a new term emerged, which as far as I can tell is a synonym for most people, and it's code generation. And I think this terminology shift says something, because code generation doesn't anymore refer to the specification. It's really just I generate code. And there's not anymore this whole idea that somewhere there's a specification, there's a user intent, and the user intent should be transformed into code or whatever is something that realizes your specification. So program synthesis in this tutorial is something very, very general and very vague. This is the algorithm that automatically transforms a specification into a program. So a program can be really anything you have in mind. Typically, it's a piece of code, right? And I think this is an important way of thinking of a program as a syntactic piece of code. But you can think of it as a system or as a chip if you want to go hardware, as a macro if you want to go more user developers perspective. And now what is a specification? Again, there's a whole range of what a specification should be. It should be something that reflects the user's intent, right? And user can be, again, a lot of different people. Some people can write logical formulas. Many people can't. So sometimes we'll talk about specification as examples, just saying, look, I want a program that does this on those examples. Or natural language description, which has been extremely popular since LLMs, again. Or even demonstration. So for a long time, demonstration was a very natural specification. Look, I want a program that does this. I compute the factorial by doing 2 times 3 times 4 times 6 and 5 times 6. So, right, so this would be demonstration. So I'll be talking somehow generally about this. We'll see that the specification is kind of one side of the story, but the sort of picture I want to paint here can be applied to many different types of specifications. So this is for the first few sentences of your introduction. Program synthesis is the oldest dream of AI. I think that's a nice way of putting it. Like, this is something we've been dreaming about since Church was already saying we can synthesize automatically circuits from their specification. For decades, it was only for delusional researchers. Now we know clearly this is not true. And there's a maybe philosophical or technological question: is this really the upcoming revolution for end users, as ChatGPT suggests, for software developers, which is another type of users? And the third question is really for hardware. Will program synthesis also make a huge impact, the same impact that it has on end users and software developers on hardware? All right. So let me start by presenting 3 program synthesis tools that really kind of marked the era of the past 10 years. And what I think is sort of lacking, or why this really shows that program synthesis is not solved. So the first, or I don't know if it's the first, but the huge commercial success of program synthesis was FlashFill. Back in 2011, so FlashFill was developed by Microsoft Excel. It's actually in your laptop if you have Microsoft, if you have Excel since 2013. So you can actually, you probably have it on your laptop. And what it does is the following. So you have some spreadsheets. So by the way, this is not FlashFill, this is SmartFill, which is Google's version of FlashFill. So you have a spreadsheet, and let's say you already have those information. And now you want to add a new one, which is hi, someone. And so you clearly see what's going on. You just take hi, and you take the first name, right? But you don't want to do it by hand, clearly. You also don't want to write the macro, because if you've ever written a macro in Excel, you know you don't want to do it. So you just write one of them, and you tell FlashFill, look, go over that and tell me what you think. So FlashFill internally, it has a small programming language, which later I will call a DSL, a domain-specific language, that's tailored for exactly these kind of tasks. And it does some kind of enumerative search, combinatorial search over this space of programs, and it eventually finds one that matches that. And it applies it everywhere. And if you're unhappy, if this is not what you meant, maybe there will be some complications, some dash or some things, then you can say, no, look here, this is wrong. And then FlashFill will search again for an example, for a program matching 2 examples, and so on and so forth. And the sales point at the time was that FlashFill gets, on 66% of the time, the program with a single example. So user intent is typically very simple on this kind of spreadsheet examples. So that was really impressive. What are the limitations? So one that I will get back to at the very end of this tutorial is something close to my heart. It doesn't know that Paris is in France. And what do I mean by this? It has no semantical information. So FlashFill and almost all program synthesis tools work at a purely syntactic level. They can take words, they can combine them, they can concatenate, cut at the 3rd character, do any kind of syntactical transformations, but they have no semantical information. So if you ask, oh, Paris is in France, where is Germany? Where is Berlin? No clue. And the second thing that may be problematic also is that it doesn't actually output the program that it runs, right? It's meant to be really for users. So there's nowhere it will write the kind of Excel code, the macro that does the transformation. And at some point, this may be a limitation. You may want to check what's actually being done, right? If your spreadsheet is just 18 rows, then it's fine. If it's 500 rows, you don't want to check by hand all of them. Okay. Now, 10 years later, Codex by OpenAI, well, I guess no need for introduction, was doing program synthesis in the following way. You can give somehow the beginning of the code, in that case, some kind of doc string that explains what the piece of code is supposed to be doing, and then it synthesizes this. Right, and well, as we know, it works beautifully. Codex was, so Codex is the kind of engine behind Copilot, and shortly after came ChatGPT, but this is all the same kind of engine. So in general, what are limitations of LLMs? They treat code as raw text. How the hell did that happen? Right? And as a result of this, but also the fact that this specification is just some kind of text, there's no logical formula, there's no example, it has no guarantees. It just you know, generates code. It doesn't have any, you don't know anything of what's out of this. And also another big limitation that we'll see kind of later down the line is that these kind of things work really well if you want to write typical Python codes or typical code that people have written all over the internet. So if we have loads of data, and actually a lot of people already did what you're asking, then the LLM will be good at doing this. If you're actually trying to find something new, LLM will not be helpful for that. So LLM will not solve program synthesis beyond the classical programs. So I want to sink that in. LLM treats code as raw text. And I think this is really the fundamental mistake, right? We cannot let this happen. All right. So I'm not saying, I mean, there's not going to be a 100% LLM bashing tutorial. This is really just about what is missing to the LLM ideas, the way LLM treat program synthesis, so that we can incorporate, we can bring in all of this, well, understanding that we have about programming language and formal methods. So then there's a third one that I want to talk about. It was BARD. So BARD was not, I don't think it had the same echo as the other ones, but did something really interesting on the demo. So they had this big demo where the chief of Google was showing how it works and was asking some questions, and then he came up with some facts, and that fact is just plain wrong. He just made it up. I mean, actually, to be honest, if you would ask me, I didn't even know it was wrong. So it says something, took the very first picture of a planet outside of our own solar system, and this is kind of not true. But he made it up, but I think it's by conflating exoplanet with something. So this fact is wrong. But the problem is really behind the scene. The problem is that LLMs, they don't know, right? They don't know facts. They learn from data. This data is biased. We have no idea where it's coming from, and it cannot point to what it actually learned. So as far as semantical information is concerned, LLM is also not the right answer, right? So if we want to have semantical information in program synthesis, LLM will fail at this. Okay, so clearly program synthesis is not solved. Good for us. And what's the goal of this tutorial? I want to present some kind of the general techniques, challenges, and perspectives of what I would call neurosymbolic approaches. So approaches that combine neural networks and symbolic approaches, as in programming languages, to program synthesis that are rooted in programming language. And so let me be a little bit more clear about this. We'll have kind of two sides. One is neural networks, and by this we can or not use LLMs, and some form of logical reasoning or combinatorial search. And we'll see that this is kind of one piece of the puzzle. And the goal, of course, is to kind of have the best of both worlds. The neural networks give us efficiency, logical reasoning, combinatorial search give you reliability. You want to have the best of both worlds. So there are many names that are coming up: neural-symbolic programming language, neural-symbolic program synthesis, neural-guided, machine-learned, neural program synthesis. As far as I understand, this is all the same idea, to combine these two things. If you see a difference, I'm interested. And it's actually a very lively topic, meaning doing program synthesis not only using LLMs, but taking advantage of neural networks. So Cygnus was a competition that kind of has slowed down, but is still a basis for a lot of what's going on in this area of research. And those are just a list of some of the tools, some of the recent tools that have essentially are doing neural program synthesis. So these two are mine, but the point of this tutorial is really not to tell you about my work at all. Actually, I will only mention one thing I did at the very end of this tutorial. The goal is really to tell you what's behind all of those tools. What is the, I'll just skip this for a moment. What is the common denominator to the tools above? And so the outline of this tutorial is I'll talk about the machine learning part, the kind of programming language part, the algorithms, so the combinatorial search or logical reasoning, and then I'll talk a little bit about perspectives. And so just to conclude this introduction with these two pictures, yeah, I kind of see two futures to what we're doing here. Either, LLMs will actually just crush every hope we have, and it's just gonna be so much better than what we can achieve with, all the tools we've developed using programming languages. And then we're just this sinking ship, hoping to do something nice and good, but just like language translation, it's going to be absorbed by deep learning. Or maybe we're just the Messiah. And maybe the way we're doing this is actually the right way, and hopefully it will, in some sense, prevail, and we'll have program synthesis that's reliable in the future, not sort of the state of ChatGPT, which is amazing, but not quite a solution. All right. Do we have any question, or can I start with part one? So it's really hard to prepare 3 hours tutorial. So there's really a lot of time for interruptions. If you have questions, comments, discussions, please jump right in, because it's meant to be flexible. Yeah, go ahead.
Show the slide with the approaches for just a second.
This one?
The next one. Yeah.
Yeah. This is by no means, exhaustive. This is the ones I know, the ones I, let's say, like the most, the ones I've worked with. Yeah, there's really lots of space there. Yeah. All right, that was the end. So part one, machine learning. So this will require no specific background on machine learning. I'm not a machine learning expert. And I do think there's a lot of interesting questions to solve really just about this part. And actually, in some sense, the machine learning part of neural program synthesis is the weak point. I'll come back to this in a moment. It's where maybe there's the most space for improvement. All right, so popular specifications, we've already sort of discussed that. Examples is something I personally like. I guess this has limitations, but one very interesting point about this is that there's a clear notion of a solution program. If you have a bunch of examples, you can just check, does my program satisfy my examples? If it does, I can call it a solution. If it does not, it is not a solution. And that is reassuring for some of us, because we can evaluate what we're doing. This is unlike natural language specification. If you just say, look, I want a program that does this, does it or does it not? You write a program, it's really unclear, right? So examples have at least this good feature that there's a notion of a correct or solution. There are two names to machine learning where a specification is given by example. The old one is inductive program synthesis, because you induce your program from examples. It's like the oldest one. And programming by example, as far as I understand, this is exactly equivalent, but this has come up somehow since Flashfield. Flashfield was using programming by example, and now it's a popular name. Now, of course, the issue with examples is that it's a very partial specification, right? If you have just a bunch of, 10 examples, you cannot specify exactly what your program is doing. So this is going to be for a very specific kind of tasks, where really examples are enough to describe what you want to do. Yeah, and of course, so the good point of natural language specification, that's why it's so popular, is that it's easy to write. Right? Any user can say, I want a program that does this or that. So here's some kind of docstring describing the problem. So what we'll say here, meaning in this machine learning part, really applies to both, although not with the same efficiency, either natural language specification or examples. So back a little bit in history, the first ideas, I think, of using statistics or machine learning came back from Solomonov in, let's say, programming language community in '89, and he was saying, let's use the specification for creating statistics. So he looks at the specification, and out of the specification, he finds some kind of statistics saying, oh, if you use this and these words in the specification, then this is likely that the solution program uses this or that or has this or that features or properties. This was already back there in '89, but it took almost 15 years to say, well, actually those statistics, we don't have to write them by hand, we can learn them. So this was the idea of Menon et al. Menon, it was to say, well, we can have data sets of programs and their specification and try to learn some kind of way of, if I see the specification, I can extract some properties from it that will guide my search. So I can extract some properties of the solution program, and these properties will allow me to sort of prune or guide myself towards a solution program. And I think what really changed was this Balog et al. Paper. This is a deep coder. That's the first one that said, well, we'll do exactly this, but we'll do it with machine learning, with deep learning. So they took exactly the ideas that were there, but they just slapped in a huge neural network, and they said, well, the neural network is learning predictions. And what kind of predictions precisely? It's learning to predict what are the primitives used in the program. So it reads the specification. In the case of deep coder, it was as examples. And from the examples, it predicts the probability of each of the primitives appearing in the program. And then this is how it guides the search. And in 2017, this was a huge improvement. This practically, this really made a very large difference. And then, of course, we all know in 2021, people at OpenAI, they said, well, LLMs are fantastic at translating, French to English. So why don't we translate specification to code? All of this is text anyway, right? So this should make you angry. But this is literally what happened. Someone sat in this office and said, hey, LLMs can translate. Why don't we translate specification to code? And, unfortunately, it works. So let me go a bit more into the details of what these predictions do and why they're so useful. So let's say this is the task that I want to solve. So I give you two. This is one input and one output. The output is a list of integers, 1, 5, 4, 2. and the output is 24. And the other one is 6308, and the output is 068. So you're supposed to look at these two pairs of examples and figure out what's going on. Well, there are actually many different solutions. Obviously, it's a very kind of partially defined thing, but the way you can look at it, it is sorting these lists. So it swaps the 2 and 4, and then it only keeps the even numbers. Right? You can actually do it either way. You can either just only keep the even numbers and sort, or the other way. Right? So this is one solution program, a simple one for this task. Now, the key idea is that we will find some kind of patterns in this specification, meaning in this pair of examples. And those patterns will tell us, will reveal which constructs are used in a solution program. So the very important idea in DeepCoder was to say the neural network is unable to output the solution program, right? Because it's 2017, people are not crazy yet. So they think we'll not be able to output the whole program. But we'll just give some kind of statistics or probability for each construct, the probability that it's being used. So here are some examples of patterns. We can look at this and realize that in the output, all the values are even, right? So this is one thing you can notice. All the outputs here are even. The outputs are sorted. Also an important piece of information. The values in the outputs all can be mapped back to values in the input. And all this kind of information is somehow what you can imagine the neural network will pick up as some kind of patterns between input and output. And by picking up these patterns, it will induce some prediction model that essentially is a black box. We don't know what it does. Those patterns are with some kind of example. It takes the specification and it gives you a distribution on programs. This distribution, you have to think of it in a Bayesian way, meaning the higher the probability of a program, the more likely it is that it will be a solution. So let me get to my example. Imagine that my prediction model is fed with this pairs of examples I had before. What it should tell me is that there's a high probability of doing, let's say, sort and filter even, right? Because it picks up that sort and filter are important primitives for solving this, because it found some patterns that respect the way sort and filter act on lists. On the other hand, reverse should have low probability because, well, there's no properties that really map what reverse does in these examples. Okay. So if we abstract this away, what this is doing is it's describing a distribution on programs in order to do this. So what we want to do is find a prediction model that maximizes, so that finds over the parameters of this prediction model, the probability that a program satisfies the specification. So you get as input your specification, and now you have a distribution on programs. Every program has a probability, with the idea the higher the probability, the more likely it is to satisfy the specification. And this, in 2017, was a very interesting middle step. It meant we go halfway. We don't output the whole program, because that would be just too complicated. Neural networks were not able to do it, and I think they are infinitely better today, but they're still not able to do it. But they can give you a lot of information. And then, you meet halfway, the second part is up to you. This is symbolic search. This is the message of today's tutorial. So once we have this distribution, we'll talk about what to do with it. But the idea is that the prediction model doesn't give you the program, it gives you a distribution on programs, and now it's for you to explore that distribution. Does that make sense? All right. So this is the intuition we should keep. The probability of a program satisfying a specification is supposed to be following this law. The larger this is, the more likely it is that the program satisfies the specification. And if you have this, this is exactly what you need to sort of guide you through the space of programs. All right, so now to the main question is, how do we achieve that, right? It's a beautiful idea to have prediction models, but how do we actually do it? And how did DeepCoder did it? And how do we do it today? So the difficulty is, of course, to find a data set. And by a data set, I mean a large collection, very large collection of pairs, specifications, and their matching programs. So if you think LLM today, you know that they just took all of the internet. But it's really still a mystery how out of the internet you can find a good data set of specifications and programs. I mean, to me, it's a mystery. And actually, this is really the main question they struggle with. And once you have this data set, what you're trying to do is just train the prediction model, essentially minimizing the loss function as we've seen it above. So that is sort of canonical. So if we dive a little bit more, there are kind of two issues that we have to solve here in creating or curating this data set. The first one is finding the data set. So now there are kind of two cases. Either you scrape the internet, but the problem is that you'll get very low quality of your data set unless you have a lot of manpower to work on it, let's say. Or you go for synthetic data sets. And this in itself is a very interesting question. It means data generation. It means how can we generate meaningfully 3 million programs in your favorite programming language? And if it's Python, okay, you can go for that. And you can find 10 billion programs, and maybe you'll find that out of those, 2 millions are interesting, and maybe you're happy with that. If you want to do program synthesis in a smaller programming language, maybe a proprietary one or one that doesn't have so much data, you'll have to go for synthetic data set. And it's a very interesting and open-ended question, how to do data generation in a meaningful way, meaning to find this data set. One concrete issue we have there is program aliasing. I don't know if this is the only term for that. Of course, when you have a specification, there are many, many programs that solve that specification, right? And so the typical example I give, maybe it's not the best one, but imagine you can go left and you can go right. And the question is, you want to go forward. Well, you can start by going left and then right, or right and then left. Those two programs are, of course, equivalent. But if you try to learn a toddler to move forward, and every second time you say, well, left and then right, or right and then left, then you will just confuse this poor kid. So you should be consistent. And more generally, this talks about programming style. What you want in your data set of programs is that there's some kind of uniform style of programming. And this, again, it's impossible that this holds in a data set you scrape for the internet. And this is a very big issue of LLMs that they have, that the type of code you get will very highly depend on what you write. And there's going to be no uniform way of sort of dealing with your code. So program aliasing has kind of two consequences. One, it slows down learning, because instead of saying, look, this is the right program, you say, well, there are two programs and they seem to be equally good. So you have to share the probability. That's one issue. So it slows learning. And second of all, it also kind of makes this programming style very random. And that is also undesirable for the output. Like, you write something, you get a piece of code, and you write something else, it's going to be a very different piece of code. And maybe you will not be happy with that. So data generation, I think, is something that hasn't been as much kind of investigated from our perspective. People do it in these machine learning tools in a very naive way. What they have shown is that the more effort you put there in creating your data set, the better the tool will be behind. But it really takes a lot of effort to find good data sets. And now all these LLM companies are all about finding good data sets. So 2 steps. How do we generate millions of programs? That's step 1, which maybe is the easiest. But the second step is almost as hard, I mean, actually harder. For each program, you need a specification. And so there's lots of literature on how to do this. This sort of looks very much like testing in the sense that you have a program and you want to test it. But testing doesn't exactly yield the best results so far. So I wanted to kind of draw your attention on this as a very important open problem in this. So this was the part about machine learning, with the emphasis that one big open question is how do we create data sets? And more that really this is something maybe we can address as a programming language people.
One quick question.
Yeah.
So I played a little bit with this, and what I noticed that often you get programs that don't even type check. Could the type check already be part of the specification?
Yes.
Has there been any research
So for this, I will need to go into step 2, where I will talk about all this typing and everything. But of course, like this will be step 1 of all of this. We programming language people, we know how to generate at least programs that type check. This we know how to do. That doesn't mean that they are interesting. If you generate random Haskell programs that type check, they will be rubbish, most of them. But at least we can ensure that, which is something, but not enough. So I'll get to more like the programming language part of this. Any more questions or comments? Or yeah.
Can you go to the previous slide, please? Okay. So it seems to me that the probability is hiding a lot of information from the original program.
Mm-hmm.
So why it is 1/2 the program 1 and the probability that is correct and program 2 is not 1/2? I mean, is there a way to explain this probability? Because they may be half correct for a number of different.
I mean, half is some kind of oversimplification. Is more like you need to share the weight, right? So if there are many correct answers, then the probabilities have to be shared. The mass have to be shared. So let's say in my personal experiments, what I found is that the more ambiguous your programming language is, unambiguous, sorry, so meaning avoiding program aliasing really helps in learning. I don't have an answer to the question you're asking, which is, can we make this a bit more specific? Can we actually give more information to which of these two would be better? I don't know how to do this. But again, it kind of will depend on how I represent programs. I mean, how we represent programs. So this is part 2. So it's a great transition, unless someone has another common question.
For this data generation problem, did you think about some language which you can use to help generation data?
Let me talk about part 2 so that we can talk about this, because I haven't told you yet what's kind of how do I represent the program. I mean, I say how programs are represented, because then that will be important for answering that question. But I'm presenting it as a big open problem. I have thought about it. There are many papers on the topic, but it's really, as I would say, a widely open problem. So if you have some ways, techniques for tackling this, I think that would be very interesting. Wait, I know. This is the French time. So we have another 40 minutes before the break. Is that correct? We have just the time to move to part 2. Okay, so programming language, and trying to address the questions that sort of you all raised. How do we represent all of this so that at least we have, type checking and all of this. So, of course, the first wrong idea. Let's do program synthesis in Python. It's really funny because 3 years ago, no one would think about doing that. It was clear that it was heresy to anyone doing program synthesis, but now we have to discuss that because actually people are doing it. So why Python is a bad target language for program synthesis? Well, it's too large and general. There's so many different ways of writing a piece of code, a piece of Python that does the same thing. And this is program aliasing. This means like we'll just end up making learning very complicated. It has a very complicated syntax, obviously. More and more complicated as time goes. And lots of, I'm kind of repeating myself, lots of program aliasing. But of course, and this is the reason why these general purpose programming languages have been chosen by LLMs, is because there's loads of training data, albeit bad training data, but So what people have been doing in program synthesis forever, essentially is using domain-specific languages, which are small programming languages that you design specifically for a set of tasks. So think of flash fill. We want to do string manipulations. I'm sorry, I thought you were trying. So you have a set of tasks like string manipulation. You design a programming language specifically for that, and that will make search much easier. That will make learning much easier. So you're just winning on all sides. Specifically, the way you can think of it is, let's do functional programming. We define a bunch of primitives, of things that you can combine together, stitch together to write a program. So you have components. Some people actually call it component-based synthesis. You have some components. Think of it as I can sort a list, I can add 2 numbers, I can filter by some predicates, throw in anything you need, being reasonable. And you have a programming language, a DSL, that's specific to the kind of task you want to solve. And this is what people were doing, have been doing, and hopefully are still doing, doing program synthesis. So an example of the DSL and how we can work with that, let's say I have a list of primitives. So I'm being slightly fancy here. I put, for instance, polymorphic types. So sort is for list of integers, but map can take any function of function t0 to t1 for any type, takes a list and applies the function to every element of that list. Right? So you can have programming languages construct as we know, successor, just integer to integer, and so on and so forth. So imagine that you just fix a set of primitives you want to use. And you say, that's what I will be using. Now you have types. This is the usual, old story that people here all know. Maybe some atomic types, generic types. You can do constructors, arrows, lists, sets, whatever you want to do. And we all know that the way to talk about the space of programs is using a context-free grammar, right? So this will be the way the representation for abstract syntax tree, these ASTs that represents. So this will be one program where at the leaves you have constants or variables, and each of these things are representing some primitives, and you just combine them in a tree-like fashion, right? So the point of this context-free grammar is that it represents the set of programs you have. So it represents the program space. And when you have this program space, you can reason about it. You can start thinking about generation, about search, about, well, of the things we like to do. So I would call this step from going from the DSL to the grammar some kind of compilation. I have some kind of picture, but I feel that I'm just preaching to the choir. Everyone knows, you know, these basic things. You have primitives, you make them into some grammar, and that means that the way you typically represent programs is as some abstract syntax tree, and we reason with this. All right. So let me go ahead. Now it becomes more interesting. This context-free grammars, we will equip them with probabilities. The idea is now, how can we combine this representation on the space of programs with our machine learning predictions? Okay, so this is a grammar that represents my space of programs. And now I will make it probabilistic by just saying every derivation, I will give it a probability. So here, the intent was to generate a program of type S. I can just start with the primitive F and then generate two programs of type S. Or, non-deterministically, a primitive G and then a program of type T. So this was, a grammar is some kind of non-deterministic process that generates all programs. You make it probabilistic by saying, with priority of 4, this is an F, or priority of 3/4, this is a G. And now what you have is a stochastic process that generates programs. In other words, this thing is a distribution on programs. It represents a distribution on programs. And I already said these words earlier when I was talking about neural networks, model predictions. So this is how these two worlds will meet, and this was really the crucial idea of the deep coder that's been reused in all the tools since then. Some form of probabilistic grammars are representing the distribution on programs that we want to explore. So now that means that any program will have some probability of being generated. And to compute it, well, you just look at every single choice you made, and you look at the probability that you made that choice, and you just make a product of all of this. So every program has a probability. This is a distribution of programs. The PCFG induces a distribution over trees, aka programs. So now back to machine learning predictions and how we can connect these two things. The idea is that the prediction model, let's say, so here I'm maybe lying a little bit, as in this is what deep coder was doing together with a set of its successors. Of course, the different tools have sort of variants on how they really represent all of this and work with all of this. There are different grammar models and different ways in which they represent the probabilistic weights, but the story is sort of similar. The goal of the prediction model is to attach probabilistic weights to your grammar. So it reads the specification and it tells you everywhere, look, this is the probability of the primitives given the context we have. So you have to think of it as I'm generating my program, and when I'm somewhere, I ask my model, my prediction model, what is the probability now that I use this primitive or that primitive or that primitive? And everything is computed by the prediction model. So what the prediction model gives you is it takes your space of programs and it sort of makes it in a nice distribution that's represented by a grammar. So here's the state of affairs. Step one was to build the space of programs. And what we said, I kind of went quickly because I know this is classical stuff for everyone here. We construct a grammar representing the space of program. The grammar is a non-deterministic process. Now, we learn the probabilistic weights to equip that grammar with priorities, make it a distribution on programs. And so that means that now we have our examples, and fixing these examples, every program has a certain probability. And what we want is just now to explore, so I would call it search through this distribution, meaning find a way to go through programs, you know, in maybe the most natural idea would be what we call best first search, meaning go through programs in the decreasing order of probability. So first you try the program that has the highest probability according to your prediction model, then the probability just below that, and so on and so forth. So you order programs by likelihood of them being solution, and you try them in this order. There's of course a lot more ideas. Yeah.
Please, the reason that you talk about probabilistic grammar as a way to represent distribution of the program is because of some computational reasons, or because, I mean, you can think, if you don't care about generation of programs, then think about the distribution of programs. But then there are multiple ways that you can do it. Something you mentioned, like some keywords appear that each of the keywords gives some probability. And then that kind of things can be perhaps used to design a model. But you have a particular choice, make a particular choice in your presentation. Is there any reasons behind this?
So I have two answers. The first is that I have lied a lot, in the sense that I'm presenting kind of the simplest version. And of course, you're right, like we can think of more complicated models that look a bit more, I mean, still look like grammars or not. But the second and maybe most relevant answer is that there's a fine line. You have three things to keep in check. The first one is that you have to have predictions that are meaningful. If your model for generating programs is too complicated, if your probabilistic model is too complicated, your predictions will not be very accurate. So you need to keep sort of the distribution of programs simple in order to have good predictions. And the second thing is, at the other end, we need to search through the distribution. And again, it should be rather simple in order to have efficient algorithms to search through a distribution. So if you have a very, very complicated way of representing your distribution on programs, it may become very difficult to search through it. And so there's some kind of trade-off to get there. And so actually, this is maybe an interesting point to make this remark here. In practice, those predictions are really not very good. None of the tools are able to do very good predictions. As in, you look at basic examples and you would imagine that it will pick up, oh, this primitive has to be used, like, you know, sorts and stuff. In practice, this really doesn't happen too well, but the predictions are, let's say, above uniform. They're above, they give you some hint, and this already gives you a huge kind of improvement. Yeah.
And isn't one of the big issues with the predictions just the fact that you can't keep into account previous state? Like, you know, every time I go to it, assuming that I just directly, because I mean, if you look at an LLM, right, it keeps track of the tokens already output. Yeah. And I feel like you could modify this pretty slightly about, like, you know, if you output a vector for each branch in your tree, you just take what you have so far and then you pick a traversal order, and now you can get much better predictions, hopefully, because you know what you've already spit out.
So I thought so too. And there are actually tools that explore this using, instead of 1 gram, using n grams. So, right, so you would remember a larger part of the context. Meaning when you generate your program, you want to say, I will encode in my, you know, in the non-terminals of my grammar, I will remember, let's say, the past 3. Is this what you meant, or?
Well, what I was thinking is more that's like, okay, say my grammar has a maximum length of n. Right? I want to output a vector that's going to tell me what's the probability of taking the next n choice. And notice this is a very slight generalization of how an LLM works, because an LLM will tell me the probability of the next token, you do beam search, right? Yeah. So now what I do is every time I output a token, right, I take the token that I output and I feed it back into the model recursively with some kind of memory cell, maybe a transformer, maybe an LSTM, maybe whatever it is. Like that, I can keep track of the context. And now the one modification I need to do to my search procedure is I have two cases. So either I can only look at the context of my parents. So for example, I can only say, okay, I chose if, and then the if is inside a while, and then inside the while, now I'm doing this. Or what I can do is I can pick an in-order traversal. So I could say that, like, for example, if, and then I'm going to pass in the whole left branch, and then I have the right. So the in-order traversal is better, but that means that now, you're biasing it one way or the other. And you have to pick a traversal because that's the order that you're going to have to do the inference in. And then so as you do it in your training data, what you do is you do exactly what an LSTM or transformer or whatever it is does, is that rather than trying to learn a global distribution per program, you're trying to learn, given a token, you want to accurately predict the next token that appears, which very well does exactly how an LSTM works. So what we're really doing is constraint generation. And LSTMs actually, so there's a whole thing of actually taking an LLM and giving an LLM a grammar. So I've done a little bit of work on this, is that you actually just take a CFG and you tell the LLM, okay, you will generate according to the CFG.
Right.
And so now what you're doing is you're actually changing it the other way around and saying, okay, an LLM needs to work with a very big set of tokens, a very big bunch of data. Now you're saying, okay, the set of tokens is very small, so we can use a much smaller model than an LLM and therefore try to do this.
So yeah, I mean, thanks. It's very interesting. This is so in some sense, is exactly like you said. We have this. This is the very kind of basic extreme approach where you have the most simple grammar model and no context, and you try to do predictions.
Yeah.
So the good thing about this, predictions are cheap, and search will be easier because you have a simple model. You go the other extreme, you go LLMs. Beam search on LLM is extremely costly. If you want to get the first 1,000 programs out of an LLM, it's going to take you.
Not that much, because the adjacent things in the beam, just like here.
Okay, so we can. I mean, I guess there's a question of scales and things, but. At least when I was playing with this, and when I was Dreamcoder was experimenting with this, and somehow the idea is that you should play somewhere in the middle. So exactly like what you're saying, but yeah. So I kind of kept it simple by saying I will take the simplest models, which in some sense make my search, my inference later, as easy as possible. But I agree that the trend is to move towards more context and bigger. Yeah. Thanks. So we're somewhere there. This is my picture of neural guided program synthesis. There are three parts. There's the prediction. So this is the neural networks. Then there's the search. So you can imagine here, this is your space of programs on which the prediction acts to kind of define probabilities. And here we have a symbolic space. So we do symbolic search, whatever that means. And whenever you have a candidate program, you can check it against your specification and hopefully get some feedback. And so now this is the kind of general picture of neural guided program synthesis. And the question is how to make this efficient. So I do believe that we're behind on these predictions. I think those predictions at the moment are really not fantastic. But the fact that they're better than nothing, better than afraid, better than uniform, already gives you huge improvement in practice. So there is a question of how to make predictions better. But there's another huge question, how to make search better. And there's a third very interesting question, how to make feedback better. Right? So imagine we have 5 examples. And you find a candidate program that solves one of them. What does it mean? How do you bias your search to say, well, that program, it was 1 of the 5. Is this actually by chance? Is this useful? Do I want to bias this symbolic space? And so a lot of papers are coming out sort of addressing those 3 issues, more or less at the same time, or not. Does that make sense?
Yeah, right. Do you assume that the program that you're generating are smooth?
So this is, I would say, an orthogonal direction, meaning so you want to differentiate on the space of programs. So here I'm not making that assumption, and the way I'm designing DSLs is it's really a symbolic space, so there's no reason to have that. This is yeah, like a very natural sort of competitive approach. I don't know how to really bring those two together. I've seen, yeah, I don't know.
Well, actually, one of the advantages of what we're doing is this very simple context-free model. Is it the weights in the context-free model, that's differentiable. So actually, the hyper program that he's generating is differentiable. So one thing that you might do is that if you want to generate a differentiable program, if you do what I was talking about and talk about like a token by token thing, the token by token predictions are themselves differentiable. And then that's actually what a transformer works, right? Is, you know, generating a word is not differentiable. Generating a probability distribution on words is differentiable. And yet a probability distribution on words can be very sharp. It can approach generating a word. And so, yeah.
Moving to part 3. So I'll probably not finish part 3 before the break. We'll talk a little bit and then take a break. Yeah, sure, of course.
Wait, the second thing you mentioned about you mean your objective in the presentation is the model for which the search can be done efficiently.
Yeah.
Then we have some results where this result say for populating grammar, the posterior inference or head inference can be done according to the and then it's not exactly posterior. You have a set of examples. You generate the program, you want to make sure that your program actually produces even inputs to the hidden output. So there's that kind of search, the mapping first follow the context, like a maximizing probability by all these specs can be done according to that time. These are there are maybe some like inside outside.
Yeah.
Can you provide it even?
No, I'm not familiar with any work that has done that. I think kind of along these lines, but
there's some context in the. I mean, some other people use that person might be here or not, but they try to distill. I mean, in machine learning, they call it this abstracting a model or distillation. So they want to distill large language model to hidden Markov model,
right?
And they try to, for hidden Markov model, many things are computationally done efficiently. So I think in that context, they try to design an algorithm which performs a bit like doing some posterior inference with some strange information about population.
So yeah, thanks. I think this we should. I would be happy to get more. I would like to say one thing. By all means, this is not mine. This is stuff I've been working on, but so far we've been talking essentially about DeepCoder Plus. So we're still like in 2020, right? So this, I mean, clearly these model predictions can be thought of as LLMs, and then you go 1-2 years later, but all of this stuff is now, let's say, classic in neural program guided synthesis, and it's really not mine. I mean, I've heard some people saying you, and I just didn't want to clarify this. I've been working on this, but this is not all mine. All right. So just like what you're saying here, your space of programs could have different properties. If it would be differentiable, then you could look at gradient descent approaches, optimization approaches. If we look at it as a symbolic space, then we can think of it as doing combinatorial search or reasoning on the space of programs using the predictions. And this, again, is a huge open field. How do we do this? Exactly like you were saying, depending on the complexity of your model, if you have, if it outputs a proaches grammar or something more complicated that takes more context, search will be maybe less efficient, but your prediction might be better. I mean, there's a lot of leverage here. So I'm focusing on this tutorial on proistic grammars because that's kind of the common denominator of what everyone's been using. And many algorithms actually can be extended to more complex models. But I agree that this is not the end of the story. We shouldn't stick to proistic grammars for themselves. So I will tell you a story that seems to be completely unrelated. And I really like it because it shows that this search question is far from trivial. And so there will be no program synthesis for a bit, there will be airport screening. The story is the following. So we came up with some algorithm, we published it, we were very happy. And then I think we thought about giving it a name. We typed the name on Wikipedia. And what came out is that this is something that's been known and used in airport screening and published in an airport defense system conference, something like this. So, and it's exactly the same idea. And it's a very simple idea, but natural, and it sort of shows the difficulty of learning against predictions. Sorry, searching against predictions. So the following example is real, as in it's been published in very applied conferences. I'm not sure it's used, but politically it's really a bit dodgy. So it's not my views. Here's the setup. You have a population. This is people entering the airport. And among those people are terrorists, right? And the question is who to scan. You cannot scan everyone because scanning takes money. So you have to sort of find some way of biasing your search over the whole population to catch terrorists. What you will assume, and I hope you see the parallel with what we're doing, think Bayesian, we have biases. And to be as politically correct as I can be, my bias will be against men against women. Men are 9 times more likely to be terrorists than women. I hope it's fine. So men are 9 times more likely to be terrorists than women. And now knowing that single information over the whole population, I want to bias my search. So I want to decide what's the probability that when someone enters the airport, depending whether it's a man or a woman, I pick it out and check if it's a terrorist. Assuming I can do this, well, whatever. So what I will be able to do is someone comes in and randomly I can say, hey, are you a terrorist? And if not, I just replay and put back the person in here. Okay. So mathematically, what's going on? We have a population X of individuals. Could be infinite, as far as we're concerned. And we have a distribution on this, which is given by this Bayesian prior. This distribution is just saying it's 9 times more likely to be a terrorist if you're a man than a woman. And we want to do sampling with replacement. This with replacement, we can come back to that later. It would be kind of annoying to say people that we have scanned, they go to a different room. In practice, you can do this, but for program synthesis, it would be really hard to say that there are programs we've already checked and programs we have. So let's do sampling with replacement. So possibly when you check something, you will possibly check it again and again, because we'll do a sampling procedure. And the objective, naturally, is to minimize, on expectation, the number of scans you do before you catch a terrorist. And this expectation is over the bias you have. Okay. So when we formalized that question some years ago, it was absolutely obvious if your bias is D, your algorithm is T. Right? If men are 9 times more likely to be terrorists than women, we check them 9 times more often. Kind of sounded like what else could happen? And the answer is no. So the naive would be D. The optimal is square root of D. So if D is a distribution, square root of D doesn't have to be a distribution, but sometimes it is. So the way it's defined is the probability of individual X is the square root of the probability of x, and you just need to renormalize. So renormalize by the sum over everyone. So in some cases, this thing, may be infinite. So this is not defined, and then it's not a distribution. But if you have a finite population, it's always defined, and if you have an infinite one that's, for instance, given by a PCFG, it's going to be fine. So you can show it's actually not very complicated, that this one, square root of d is optimal. I'll give an example in a second, maybe or you want to ask a question?
Well, yeah, I'm going to be saying something very dumb here, showing my lack of understanding of statistics, but wouldn't you want to, okay, assuming that, there's, in real life, there's the concerns of unpredictability and adversary and so on and so forth, but in real life, wouldn't you want to only scan the more enriched population until you run out? It's assuming I have some ore that has lots of gold and some ore that has a little bit of gold. Wouldn't I want to process all the ore that has lots of gold before I even touch the ore that has a little gold?
But I will not assume that I can separate these two. They will just come one by one.
Oh, yeah. So, okay. So, but then what's the strategy here? So are you saying that first you're going to do the check, and then based on square root of d, you're going to determine whether to go ahead?
Yeah.
Okay. That's yeah.
So the theorem is like this. If you have a distribution d representing your bias, well, there are kind of two cases. Either the square root distribution is infinite. So this normalizing factor is infinite. That means you have a not very, the tail is kind of thick. And that means that you're doomed. The loss will be infinite, meaning on expectation, it will always take you infinitely many scans before you find a terrorist. Now, if this is well behaved, if this is finite, then square root of d minimizes the loss, meaning it's the one distribution, one of the distribution that minimizes the expected number of scans you do before you find the terrorist. So by the way, terrorists are solution programs, population are programs, so that we're politically on the same page. So to make it concrete, let's take the simplest instance of this square root sampling theorem. Let's say I have a population of 2 people, which I will call head and tail. And they have a bias P1 minus P. So think of it this way, with priority P, head is the terrorist. With priority 1 minus P, tail is the terrorist. And now you have to choose a distribution D prime, P prime 1 minus P prime. So you have a single parameter P prime to optimize. P is fixed, you're optimizing for P prime. And what you want to minimize is the loss. So what is the loss? The interesting thing is that what you will effectively do is you will throw coins repeatedly with replacement. So you throw them again and again, and maybe you will throw the same over and over again until you hit the one that's a terrorist. So how long does it take, assuming the terrorist is head, which happens with priority P? How long does it take when you throw your coin with priority 1 of P prime, sorry? How long does it take before you hit head? Well, on expectation, the Bernoulli distribution is 1 over P prime. So this contributes to P divided by P prime, and for tail, it's 1 divided by P, 1 minus P divided by 1 minus P prime. And when you optimize this in P prime, this is a quadratic equation. And the solution you get is this square root here, this is the square root, and this is the normalizing factor. So the idea is that the square root thing is kind of pushing the bias a bit more towards uniform. So men are 9 times more likely to be terrorists. But if you really hold to these beliefs, you will check men way too often, and you should actually be more closer to uniform that will kind of smoothen your search. So the solution is, if men are 9 times more likely, then you should screen them 3 times more often. Some people say that it shows that racism is useless, right? It means that your biases, you shouldn't hold to your biases, you should smooth them a little bit. So maybe there's a positive message to it. But what it really shows is that having a distribution on programs and searching through it here with a very basic algorithm, which is just sampling with replacement, is not as easy as it sounds. And if you have a complicated probabilistic distribution that's given by, I don't know, whatever crazy model you can think of, the square root of D may be non-trivial to compute. There's a nice outcome to all of that is that for probabilistic context-free grammars, actually square root of D is easy to compute. You can compute it. It's another probabilistic context-free grammar. But in general, this square root of D distribution may be non-trivial because of the normalizing factor. So let's stop here, and we'll talk about other kind of inference algorithm after the break. And I'm happy to take questions now if you have some, or we can take them. Thanks. So we start on time, so we have like 40 minutes break. I think. There's like half an hour officially, and we're 10 minutes early. So we can get coffee first. Yeah,
you should have the AST with the probabilities on the grammar stuff. I wonder is this probably they compute it top down or bottom up?
Where so where exactly can you?
At the very beginning, you had a tree with probabilities on it. Yes, yes, like that.
So so here there's something I haven't said. What I'm sort of assuming without saying it, and this is what I get in practice, is that those grammars are deterministic. So there's a single way of generating a program. If you, for a given program, there's only one derivation that defines.
Okay.
And this is what you get if you do this type checking business. So this distribution, this grammar is always deterministic. If it is deterministic, then it doesn't matter. Bottom up or top down will be equivalent.
Okay.
If it is non-deterministic, then this is two different models. And for now, as far as I know, everyone has run away from non-deterministic grammars. They are more expressive, but they become, I mean, they have all sorts of.
The grammar looks deterministic, but the amount of time you instantiate this grammar with a program sounds like non-deterministic if you're putting a probability on it, right?
Yes, yes, yes. Yes,
So
yes, yes. So it's but for the search, I mean, for what I will talk about now, it actually makes a lot of differences that this is deterministic. You need this to explore sort of efficiently.
Okay.
So yeah.
I guess I'll wait the second part.
Sorry?
I guess I'll wait for the second part.
Thanks.
Thank you very much.
Yes.
So you mentioned when you talk about programming, you're saying,
Sorry, I just need to I need to plug it before it dies. Otherwise, I will be very embarrassed. How do I do this actually? Yeah. Go ahead. Sorry.
You mentioned programming being a big problem.
Yeah.
One of the biggest. One of the, as I understand it, one of the reasons that these, especially textual approaches, are very successful is that
it's not exactly that.
one of the biggest sources of
the Bayesian we do the whole in a that we then kind of the evoke is
one of the biggest sources of this is output. It's like all of our, any pretty much any language we're doing synthesis in, right? Programs are equivalent to reading it.
Yes.
And
But that's the ideal.
So these, well, I mean, they're just like any functional. I rename all variables and reserves.
Yes, yes.
Right. And so if that's not the case, then
some other cases we use
these textual approaches exploit they somehow break they somehow gain by breaking essentially renaming. So what's the right? I can understand why that would make sense I can understand why that would lead to performance improvements in the sense that we have lots of data drawn from humans write programs that breaks the symmetry in a particular way because response to things in their heads. Is there a more fundamental semantic model of why? Why breaking? Like what really is this extra information that exists in the sequence of symbols shows like shows for every sort of free symbol in your program. Why would one choice on if you could generate why is that? What can we say about our what can we say about the data generating process such that or about like this semantics of this process as a whole? Why do names matter? Why should names matter?
I think somehow it's a bit of we're trying to fit a circle into a square issue. That is, we're trying. I mean, the way we represent, we generate things out as sequences, and programs are not sequences; they are trees that need to relate to past and future. And so this is this issue that somehow we have to generate them as sequences, but they are fundamentally trees. And maybe that's just, we're trying to circle around that.
Well, sure. Well, I mean, I think that's somewhat, I mean, you can imagine that seems sort of orthogonal. Is there like a, is it somehow that like what matters is like fixing the choice of symmetry breaking across all programs that we want to synthesize.
But this is I mean, this thing becomes quickly undecidable. For instance, here's a stupid example. Plus is commutative. So you want to say if I have A plus B as a program, then I don't want to try B plus A. But if you manage to do that, breaking symmetry, it means that you found the total order on the set of all programs.
Right.
And that clearly will not be possible on many. I mean, as soon as your programming language is non-trivial, ordering it completely, totally, is just too hard. So, and I think this is just a basic example of that. So, I think we will, like, this cannot be achieved. This is more like, this is the ideal, and we want to move towards that. I don't know what's the right approach. It becomes a.
What are new topics? What is the nature of the data generating process such that some one particular there should exist a particular choice of name, like renaming, so such that it's easier to learn or it's easier to find the right program.
I think it's so okay. At least one thing I can say is that functional programming kind of helps you by, I mean, reduces this question as opposed to other programming languages that have variables that they kind of iterate over and stuff. But yeah, I don't know. I think that's a very interesting question. I don't know. And I expect that we will hit a theoretical wall, as in there is no optimal order, or there's no optimal way of doing it, theoretically, but there is some sort of, I mean, practically reasonable way of doing it. So actually, one thing I was doing recently, I mean, it's almost finished, is trying to incorporate all these constraints in my program space. So let's say I want to say that plus is associative. So I want to say any program I will ever generate, plus should be associative to the right. I mean, and no, I should never ever generate a program that's associated to the right with a plus. This I can do because this
want to canonicalize your program.
Yeah.
Up to associativity.
Yes, so for some constraints like this, I can do. Addition is a counter, I mean, commutativity of addition is a counterexample because it would sort of mean that you.
Right.
So somehow what I can do is I can do this as long as constraints are expressible in grammars.
Right, but there, I mean, for some of these, like, or, you know, the plus is interesting in contrast to namings because there is a sort of an obvious, well, there, you know, one can imagine a sort of an obvious choice, an arbitrary, but it's easy to make a choice for a canonical form, right?
Yeah.
Or, fully right or fully left associativity, whatever. Right, but for names, that's not necessarily the case. So why the, you know, kind of why would that matter? Why is that? How could that help? Procedure?
Good question, but very good question. I don't even know how to ask that question, sort of in a theoretical way, but I would be interested in having a way of just asking the question.
See,
Thank you.